Hello everyone and welcome back. This is Sritanish and in this video we're going to talk about discrete Fourier transform. First, let's take a look at the mathematical expression for finding DFT coefficients. AK equal to 1 by kaplan, sigma n equal to kaplan minus 1, n equal to 0 to kaplan minus 1, x of n into e power minus j 2 pi k n by kaplan. Now the analysis equation of DFT is given by x of k capital X of k equal to sigma n equal to 0 to kaplan minus 1, x of n into e power minus j 2 pi k n by kaplan. And since this equation is given by x of n equal to 1 by kaplan, sigma k equal to 0 to kaplan minus 1, x of k into e power j 2 pi k n by kaplan. Now the kaplan here is the length of the x of n, the original signal, and it is pretty interesting to see that both the length of x of n and x of k are the same, that is kaplan, as here x of k is also ranging from n equal to 0 to kaplan minus 1, the same as x of n, which is ranging from k equal to 0 to kaplan minus 1. Now moving on, DFT is usually calculated in matrix format. Capital X equal to DFT matrix W into small x. Capital X and small x both are column matrices of dimensions capital N cross 1, whereas the W is a square matrix of dimensions capital N cross capital N. W is it's the DFT matrix basis matrix. It is a representation of this value e power minus j 2 pi k n by e power minus j 2 pi k n by capital N, as k and n both vary from 0 to capital minus 1. In W matrix, small n value varies along rows, columns, and small k values varies along columns, but it doesn't matter as both are same. I mean both vary from 0 to capital minus 1. There's that, and this is the representation from time domain to frequency domain. This equation, synthesis equation. The main difference between DFT and DTFT, discrete Fourier transform, and discrete time Fourier transform is that in discrete time Fourier transform, owing to the highly aperiodic nature of real life signals, the output in frequency domain is continuous, but which is not the case in DFT. In DFT, the frequency domain output is also discrete, regardless of the frequency aperiodic nature of the input x of a real life signal, time domain signal. Now moving on, the experiment here is to find the beats per minute of a given PPJ signal using both DFT method and autocorrelation method, and compare them. The given PPJ signal is sampled at 25 Hz and is recorded for 3 seconds. Now let's take a look at Arduino code. This is the Arduino code for calculating the beats per minute of a PPJ signal. Since the signal is recorded for 3 seconds at 25 Hz, there are 75 samples. There is one thing to be noted here. Arduino does not have the facility to present complex numbers. So what we do is the DFT matrix consists of complex numbers because of e power minus j 2 pi k n by kaplan. So what we do is we split the matrix into two matrices, one consisting of the real values and one consisting of the imaginary values. E power minus j 2 pi k n by kaplan can be written as cos 2 pi k n by kaplan minus j sin 2 pi k n by kaplan. K is the row number and small n is the column number, and kaplan is the total length. Here it's 75. So y consists of the real values of DFT matrix, and z consists of the imaginary values of the DFT matrix. Y plus jz gives us the original DFT matrix. So here we apply the moving average filter to smoothen the signal. This is the code for DFT matrix. Y consists of cos 2 pi row into column divided by 75. Z consists of minus sine of 2 pi row column by 75. So the idea here is to calculate the magnitude spectrum. Magnitude spectrum can be calculated by multiplying the given vector. The P is the smoothed signal, output of moving average filter, Magnitude spectrum can be calculated by multiplying the given vector with real and imaginary vectors, real and imaginary parts of the DFT matrix separately, squaring them and adding them and obtaining the square root. That is the actual basic idea of obtaining the magnitude of a given complex number. So in this video we are going to find the magnitude spectrum of a given signal, and from the magnitude spectrum we should find the peak index of the highest frequency component, the index of the highest frequency component. That gives us from the index we're going to find the corresponding frequency domain, which is found by multiplying the given obtained index with fs by Kaplan. Fs here is 25, Kaplan here is 75. So we're gonna divide the obtained index by 3 to find out the frequency, beats frequency. That multiplied by 60 gives us beats per minute. Sorry about the disturbance. So yeah, that gives us the bits frequency multiplied by 60 gives us the beats per minute of the PPG signal. So let's take a look at the plots. This is the plot for signal, the 75 samples, and this is the magnitude spectra from Arduino code, from the Arduino IDE. And let's take a look at the MATLAB code for the same. In MATLAB we can represent complex numbers, and so there's no need for taking two matrices. The same idea here. Take two for loops and multiply cos and sine. Cos 2 pi kc by n minus j sine 2 pi kc by n. K is the k from the formula, c is the small n from the formula, and n is the capital N from the formula. Now this is the MATLAB code, the same, but it's relatively short here because we don't smooth the signal, and here, and we multiply the given signal with KST, the DFT matrix of required length. And here we also convert the do inverse Fourier transform and obtain the original signal. Let's take a look at the graphs obtained in MATLAB. This is the MATLAB plots. This is the original signal, and this is the DFT in K domain. Here the index is 7, peak index is 7, the same as obtained in Arduino coding. This is in frequency domain, that is K divided by 3 as explained previously. Here this is the original signal, and this is the inverse Fourier transform of DFT of the original signal. We can see that we have obtained it pretty much efficiently, except that, but we can see the obvious changes here in this area and in this area. So yeah, moving on. The value of beats per minute found from DFT method is 80 beats per minute. Now let's take a look at the autocorrelation function method as discussed in previous videos. Now this is same as the previous videos. We find we first smooth the signal. We find the autocorrelation function, and we find the first zero crossing, and then we find the index of the second peak from the first zero. The first peak in the first zero crossing gives us the index of second peak. We find the time period, and then we fs into 60 divided by peak index gives us the beats per minute. So yeah, from this we get the value to be 71.43. The beats per minute from autocorrelation function method is 71.43. And let's take a look at the plots. So this is the plot for autocorrelation function in Arduino coding from Arduino IDE. So let's conclude. From DFT method, the BPM of gain PPG signal is 80 BPM, and from ACF, the BPM of gain PPG signal is 17.43 BPM. The error is around 10.725% for between the both of the methods.